Hello everyone, I'm glad to try to solve this exercise. It's from someone on the Facebook. So I'm just gonna try to fix this thing here. Just hold on. Okay, I hope this works now. Okay. Now, myself as someone with who stays with the books, I really consider this as an opportunity. So, and it took me hours actually to think in this whole thing. It wasn't quick at all. So let's try to do this thing. First, question number part A. With what probability is the ith symbol of the first transmitted message the same as the ith symbol of the second transmitted message? First, here they said ith symbol or ith bit. Okay, why bit? Because it's either 0 or 1. So the ith bit, actually we have the sender or the origin, and we have the receiver. The sender actually sends his message twice. So, and the message was mainly made of n bits, n. This is the first, the second, and this is the nth. And it was repeated again, the first, the second, and this is the nth. Okay, am I still recording? Yes. So, and each bit has a probability of being perturbed p. So it could be like this bit, if it was originally 0, there's probability p, so it becomes flipped to 1. Or if it was 1, probability p becomes flipped to 0, and they have to be all independent. So for example, this message went through a transmission line. You know what? I don't know. I think you came from the one who asked this question came maybe from the engineering background, probably engineering background, transmission, something like that. We passed this message, actually the two messages in the transmission line, so they may become perturbed, and they may become, well, when both of them are the same, it's considered as correct. It is possible that they are both the same, but they are actually not correct. Now, in this whole exercise, for example, part A, with what probability ith symbol? Now, it really doesn't matter that we are talking about ith. It could be, for example, the second bit. I'm gonna consider the question as being for the second bit. So what is the probability that the second bit becomes actually, if we received here the same second bit? This is the first, this is the second rank, the second bit. So what is the probability that we have received the same thing here, 0, 0 or 1, 1? Now, what I want to say is that we have to agree that the origin, it's here it is either 0, 0 or 1, 1. It is not possible to have 0, 1 or 1, 0. Why? Because the origin guy, the guy at the origin, actually is he's the one who is making this thing happen. So he actually puts here 0, here he puts here 0, no error here. The error comes from example from the transmission line. So it is either it's either 0, 0 or it is either 1, 1. So when this is on the origin side. Now when we ask about this, am I still recording? Yes. Now when we ask about this question particularly, when they said like what is the probability that we have received the same. Now who are we? We are the receiver, okay? So we are not the origin. We are the receiver. The receiver mainly does not know what the origin guy, the emitter, I mean, made his decision, either 0, 0, 1, 1. He doesn't know. So at the receiver side, the probability that this guy made here 0, 0 or 1, 1 is actually half. The probability that this is 0 is half, and the probability that this is 1, it's half. Okay? Okay. Because it's simply either 0 or 1. The origin guy, the emitter, can simply choose either 0 or 1. This is it. Now, what could happen right now if actually this whole thing passed through the transmission line, and say now we have a we want them both to be received the same, so it's either 0, 0. So in this case, the probability here, the probability that that we obtain 0, knowing that we had 0, is actually 1 minus p. Okay, and the probability to obtain 0, knowing that we had 0, is again 1 minus p. What could happen? What is the other possibility? It's that 0, 0 emitter, but at the receiver side it was 1, 1. So it was perturbed here and perturbed here. What's the probability that we obtained 1 such that it was here, for example, was 1? If this is the first one, it was 1, such knowing that it was 0 is p. Obtained 1 knowing that it was 0, it's again p. So likewise here, 1, 1, p, let us say 1 minus p, 1 minus p, and we obtained it remained the same, 1, 1, or 1, 1, and p, it flipped to 0, 0. So actually let us reframe the question again. The question says, what is the probability to obtain, for example, the second symbol here and here the same. So it is the probability of this case or this case or this case or this case. Okay, so the probability of this case alone is what? It is probability to send 0 times the probability to obtain 0 knowing that it was not perturbed. Okay, it's like probability, it's actually probability to obtain, for example, it is the probability to obtain, I mean it is this thing with the half thing. It is actually the probability to send 0, okay, send 0, like the emitter, the origin 0, intersection the probability to not flip, knowing that it was 0, we send 0. I'm sorry, I'm saying intersection, so it is not flipped. So it is a probability to send 0 and it was not flipped. Okay, this thing, only this thing, it is half times 1 minus p. So why? Because why is it like that? Because probability to send 0 times probability not flipped such that it was 0. Now probability not flipped such as 0, it's actually probability of not flipped, because I think they are independent. I mean, we do not care. The probability not flipped, whether it was 0 or 1, it will remain always 1 minus p. Okay, so it really does not matter here, because these two guys are independent. These two guys are independent, but we do not care. We won't stop, we won't pause too much in here. So it is half times 1 minus p. Okay, this is probability, and this is 1 minus p. So this alone is 1 minus p, Now this whole scenario is what? It's half times 1 minus p. This is for the first one. Oh, I'm sorry. This all this is, please consider the whole this as one case. So it is it's really wrong to consider them independent, because they are not. This 0 and this 0 are always the same. So let's consider this thing as one case. So let me put this better. And the first one not flipped, and the second one not flipped. Intersection not flipped the second, not flipped the first, not flipped this one, not flip this one, the one of the first message, and not flip the one of the other message, and not flipped the one of the other message. So p0 times pr not flipped times pr not flipped, not flipped. And again, all these are independent. Being flipped here or not flipped here, or they're all independent, and being 0 or not 0 is again all independent. These three stuff are independent, okay? So times 1 minus p. Now, really, actually, it's really easy to write down this thing, but it is really tedious work to think about each and every idea. It is really, I don't know what to say. It took me really hours to do this. Okay, so it is half times 1 minus p squared for this thing. Now for this thing, likewise the same idea. Now for this thing I'm gonna write it down quickly. So it is half, or else our video will take an hour long. Half times p squared. For this thing it is half times 1 minus p squared. And for this thing, it is half times p squared. Now, we have these four cases. So, it is either, yeah. So I wanna add them all together, plus this, plus that, plus that. But am I missing something here? I know it is correct to add them, but shouldn't we say that we cannot add them? They must be independent. I mean, they cannot happen at the same time. This is what I want to say. Because why can we add probabilities together? Because this thing and this thing cannot happen at the same time. They cannot intersect. They cannot intersect. Okay? For example, when you say probability that A union B equal probability A plus probability B minus probability of the intersection. So this event and this event cannot intersect, and cannot intersect with this one. Why? Because they are simply different. This is 1, this is 0. Done. They cannot intersect. I mean, they are not the same. They are not the same. It is not like as if this event here, for example, has 3 cases, and this event here has 3 cases, and we have 1 case in here which is the same as one in here. No, it's not like that. It is simply this case is not this case, so intersection is 0. This is why we can add them together. I'm telling you, there are a lot of ideas that come into the mind when we try to solve something like that. So this is the answer, and it is a lovely answer. It will be half common factor here and here. So the half will disappear, if you like. So it will become 1 minus p squared plus, and this one plus p squared. So this is the probability that for example, the second bit is received. The second bit here is the same. Now, what is the probability for the first bit to be the same? It is absolutely the same. It is the same because everything is independent here. Okay, I mean, the first bit being perturbed, being affected, has no relation with the second bit. So the probability of the first bit is again like that. What is the probability of the third bit? Like that. The fourth bit like that. the nth bit like that. So and since they are all independent altogether, so probability to have identical message here and here is a probability of the probability of the first bit to be identical, which is this one, and I'm gonna say this ID1 and ID2 for the second bit. So the second bit the same, and ID3, I mean identical, third bit, and IDN. And since they are all independent together, okay, so it is this one times pr ID1 times pr ID2 times pr times pr IDN. So it will become this thing to the power n. It will become 1 minus p squared plus p squared to the power n. Now, what do I want to say again? Okay, why have I chosen here this to be intersection and why didn't I not say knowing that? It is intersection because I'm studying a case. Okay, a case. I'm not saying that knowing that I made a 0, knowing that I made a 1. No, I took it freely. Okay, so it is all intersection. Type. Now let us try. By the way, I want to say that another student can actually get the same answer by using another technique. Using another technique. If you want, I can try to solve it in the other way. Actually, I accidentally knew that this can have this. We can reach the same in another technique. But 0, 0. If we obtained here, it was flipped here, not flipped here, flipped here, not flipped here, both flip, both not flip, both flip, both not flip. Yeah, okay. Okay. Let me try to explain how the other method. It is really interesting. It's all for the part A. Okay. Now, how to let me get a. Okay. Listen. What is the other method? It's either to say that these two for the first bit. For example, say it could be either both flipped or both not flipped. For the second bit, it's both flipped or both not flipped. For the third bit, both flipped, both not flipped. Okay? And we already know that these two guys are always the same, 0, 0 or 1, 1. 0, 0, 1, 1. 0, 0 or 1, 1. So this is by logic, it is like saying both flipped or both not flipped for the first. Both flipped, both not flipped. So what are all the possibilities? Actually, here we come to the combination. For example, how to think? It is, for example, let us assume that they are all not flipped. So not flipped, I'm gonna say f bar, not flipped, f bar 1. So the first one was not flipped. The first one here was not flipped for both, not flipped. It could be this intersection f2. For example, let me say that f2 both again not flipped, intersection all not flipped. Okay, this is one case, fn. Or it could be that the first one, for example, not flipped, intersection, or la, the first one, no, the first one flipped, intersection, the second one not flipped, the third one not flipped, and the last one not flipped. Or it could be the first one. Now I'm gonna focus on all the cases where only one is flipped, only one is flipped. So it is now F1 bar, F2 now is the one that is flipped, F3 not flipped, not flipped, Fn not flipped, F1 bar not flipped, F2 not flipped, intersection. The last one, the before last one is actually not flipped, and the last one was flipped. So this is only one flipped. Now we are gonna take the cases where only two are flipped and the rest not flipped. Now three not flipped and the remaining not flipped. And what is all this? Actually, considering two, it is really useful to make it to the two. For example, F1 and F2, both not flipped, but the remaining, I'm sorry, both are flipped and the remaining not flipped, not flipped. Or F1 and F2 not flipped, F3 flipped, F4 not flipped, and the Fn not flipped, not flipped. And so please consider here that there is no order. I mean, there is no use to say F2 here or F1 here. It's only one case to consider. And all this should remind you of of the combination, which is, for example, what is the number of cases here? When we have these two guys, only two among n. So it is n2. Or what we sometimes we write it down like this. It's a combination. This is a number of cases. Okay, which is factorial n over factorial n minus 2 times factorial 2. This is the number of cases. For the three guys, it is n3. And for the n minus 1 guys, it is n minus 1. And for the n guys, it is n0, nn. Yeah, and for the one, or for the only one has flipped, it is n1, and for the zero flipped, it is n0, which is equals to 1, and this is equals to n. Count them down, it is n. Am I still recording? Okay. So this is what am I doing here? I'm doing the number of cases. Okay, this is fine. So what is the probability of this one? I mean, what is the probability of this one? It is. What is the probability? It is the probability of this one times probability of this times, because they are independent. What is the probability of this being not flipped? It is. What is the probability of this being not flipped? Not flipped. Not flipped. Not flipped. It is 1 minus p squared. It is all this. It is all this plus all this, which is equal to 1 minus p squared. It is this one plus this one. So it is 1 minus p squared. What is the probability of being flipped? It is these two guys, which is p squared. Okay? So it will be, all this will be like f, this one will be f, it is like probability of all being not flipped. I don't know. I don't want to get into much detail in here. I'm gonna write it down really quickly. It will be something like this. It is a summation of this and this and this and this. It will be listen, the probability of this one, it is the same as the probability of this one. Why? The probability of this one, it is the probability of only one not flipped times the probability of of one flipped times the probability of times the probability of not flipped to the power n, and this is to the power 1. While here this probability of this thing, it is again this. The probability of this thing, it is probability of flipped to the power 2 times probability of not flipped to the power n minus 2. So in general, it will be probability k times probability n minus k. So probability k times probability n minus k. And this case is different than this case. Okay, so we add this probability many times. How many times? This many times, this many times, this many times, this many times for this one. So it will be like that. N k. Okay. And k, and k varies from 0 to n, like here from 0. Am I doing something wrong? This is probability of f bar, and this is probability of f, if you like. F bar, k, 0, right? Okay. Okay. And the probability, am I doing something wrong? Probability of f bar? Yeah, probability of f bar, which is 1 minus p squared, and probability of f, which is p squared. Okay, and this is what we are looking for. And this thing, we have a beautiful formula. Here it is. You find it in Wikipedia. It is called binomial sum or binomial formula. Go to the article called binomial underscore coefficient. Go to the section called definition and interpretations, and you will find this formula. Okay, I told you I spent hours on this. So it is this thing plus this thing to the power n. This is the answer. This is this thing plus this thing. It is 1 minus p squared plus p squared to the power n, which is the same answer we got. It's the same answer we got here. Okay, we got here. And this is the probability of having what am I doing? I think I have answered on 2 questions on the same time. Maybe I accidentally mixed 2 questions, because the answer to question number A is only this, but the answer to question number B was this. Okay, so I was discussing part B without me being aware. Okay, that was the answer for part B, and that was actually the answer for part B. Okay, now comes the part C, but I'll upload this video. Okay, or shall I? It's okay, I'm gonna continue. It's okay, I'm gonna continue, it's okay. So now I really hope that this could help someone. Now let us do the part C. Find the probability that despite the coincidence, despite the coincidence of the 2 messages, the information turns out to be erroneous. So we have coincidence and intersection erroneous. Coincidence and intersection erroneous. So what is the probability that the 2 messages completely coincide? This means okay, I made an intersection and not knowing that. I didn't make a slash for knowing that, because the word despite mean that it happens. It's like and. It's like and, A and D, and is an intersection. So this is why I made an intersection. Find the probability that despite the coincidence, the information turns out to be erroneous. What is the meaning of coincidence? It is actually they coincide. I'm sorry. They coincide means that they are identical. Okay, so means that they are identical, completely identical. Okay, and we know the probability of being identical is this thing to the power n. We made it. So they are asking about this, but they are making another thing, which is to be erroneous. Being erroneous means that actually we do not want all the cases we stated. We do not want all these cases. They want them to be erroneous. Sorry, what am I doing here? No. Being erroneous. It is like okay. I figured out actually 2 ways to do this. It's too messy in here. Okay, let me stop this to upload it. I really don't want to. Okay, we continue with the